Okay, good morning.
Good morning.
Can you see the presentation okay? Let me get it.
Yes.
Good, good. Okay. Okay, so today we will do some more on properties and characterization. Oops, let's see. Here we go. Oh, here it is. All right. So we started, wait a minute. Yeah, okay. So last time we talked about some of the microstructural properties about the structure. So we talked about density, porosity, pore distribution, and surface area. And I didn't get to imaging methods, so I'll talk about those today. And then I will also talk about mechanical properties and spectroscopic. Really, I'm going to talk about optical properties. And I will not get to thermal today. I will do that at the beginning of the next week, unless I talk really, really fast, but I will not do that. We'll try to talk slow. So last time we talked about density, and the main thing there was because of the porous nature of aerogels, and it's true of any porous material, you need to specify, are you doing a bulk or a skeletal density? And it can be hard with irregular shapes. And we talked a little bit about ways to do that. And then we talked a lot about understanding the pore distribution and the porous nature. How do you measure surface area? And to do that, we use gas adsorption and BET theory. And that idea was we condense a layer of gas, of known gas, on the surface of your material, and from that you can calculate how much surface area there is. And then as you add more of the gas and it condenses, you can fill all the pores in your material. And we used BJH theory to determine the that should be size of pores was what we were able to get out of there. And equilibration time is important. And then for aerogels particularly, seems to work better to use the desorption isotherm. Remember, we adsorb and we desorb. So that was last time, and that's in the file from last time that I sent to Professor Buratti. Okay, so we'll do some work with imaging methods. And this is another way to learn more about the microstructure and what it looks like. And the three I'll talk a little bit about are scanning electron microscope, or SEM, tunneling electron microscopes, or TEM, and atomic force microscopes, or AFM. And there are other techniques that can be used, but I'll just talk about these two. So the scanning electron microscope, I don't know why this is so. Yes. I don't know if I can. No. Can you see the top where it says scanning electron microscope online? Yeah. You can see. Okay, yeah. Maybe I just. Yeah.
Yes.
Okay. Okay. So I don't know. Have any of you used a scanning electron microscope? Has anyone had one to use? Oh, so basically you take a focused beam of high energy electrons, and you, in this particular application, it looks like a insect of some sort. This is a picture from Encyclopedia Britannica, but you shoot those electrons at your specimen, whatever it is, and you collect what comes back off it. And you can get information about the texture, the morphology, like what the pore structure looks like. If you have energy dispersive X-ray along with your SEM, you can determine chemical composition. and the crystalline structure from using an SEM. One of the difficulties with an SEM is sometimes you have to prepare your surfaces by sputter coating them with some kind of metal, but that can be problematic because then if you're coating a very nanoporous, particularly for aerogels, a very nanoporous structure, it can mask the features, so you won't see as well what you want to look at. On the other hand, silica aerogels are very difficult to image because they're insulating, so it's a trade-off between doing that. We have done some sputtering coating, but we don't do it anymore, but we also don't get great images, so it's hard. So I'm going to show you sort of some examples of what, let's go to my screen. Looks good there. Anyway, this is a hydrophilic silica aerogel, and so the scale bar is 1 micrometer or 1,000 nanometers is what we're looking at. And this is a hydrophobic silica aerogel, and the scale bar here is 200 nanometers, so it's a little different scale from here. But we use this to try to see the structure of the aerogel. So this is just a small portion, right? It's not a very big piece of the aerogel. So you have to look at a lot of different locations when you are imaging the aerogel. But we can see, we see some porosity here. You can see this is sort of the typical aerogel structure you might see. We say it looks fluffy, cloudy, and this is typical of what you see with silica. It's hard. Again, I'm going to show you some other things that we image, like the alumina, which is a little easier to do. But this is typical of a silica aerogel. It is difficult to characterize. We could say, this looks like a pore. That's a big pore. That would be a macro pore. It is difficult to characterize because we're only looking at a little piece. So the gas absorption techniques give us an average over the whole sample, but this is just a small amount. So you have to look at your sample in many different locations. So with the reason I'm showing you this is here is a hydrophobic silica aerogel that we made using a different precursor, and it has a very different structure that you can see. It looks, I don't know how to describe, more pointy. You can see the difference between this, and these structures repel water. And part of the way they repel the water has to do with the chemistry that Professor Carroll talked about a little bit. It also has to do with the structure. The way it is, it's kind of pointy and it pushes the water away. So we were able to use SEM to sort of look at these materials. We also used SEM to look at our ability to entrap copper nanorods and copper nanoparticles in silica. And so these two are images. This is an SEM image, and the scale bar on that, I think, is 2 micrometers. The scale bar on this one, it's hard to see. It's bigger. Oh, it's on the thing. This is 800 nanometers. This is 800. I'll explain these two in a minute. So this scale bar, no, sorry, this is 1 micrometer. So we had a project where we were making aerogels, and we wanted to see if we could dope the aerogel with different metal particles, nanoparticles. And it's difficult to do because they will agglomerate and stick together. Now, first thing we did is these copper nanorods, which are shown here. they didn't agglomerate. That's just a single nanorod. That was the size. We wanted to see if we could get it in the aerogel. Again, this is a very small piece of that aerogel, so we had to search in many different locations to see if they were entrapped, right? We figured they were entrapped, but we didn't know because we processed them and we released supercritical fluid, and it's possible the nanoparticles go with that. But we were able to do that with the nanorods. And then this is, let's go to this slide first. So you can use energy dispersive X-rays or energy EDX or energy dispersive spectroscopy, EDS, this one. And so it can be used with SEM to identify composition. So when you use scanning electron microscope, you have an incident beam on your sample and of electrons. And so they reflect off, and depending, they scatter off. And there's a lot of information that comes from that. One is called the backscatter electrons, which tell you something. And you also get X-rays come back off of that. And so you can use an X-ray detector to capture that information. And so there are a couple of things that will give you. You can look at a sample and have it tell you what its chemical composition is. And you get something like this, which sort of tells you, you can extract a spectra like this, which tells you what chemical there are in there. So this particular one has some copper and some alumina and some other copper. Now these X-ray spectra have signature peaks at different locations, and some things can overlap, so it's not always perfect, but if you know what you put in, you can search for that in your sample. So this is another, what I also will show you. The EDX would sit here off to the side of your SEM and collect those X-rays. And so our system has that, and we've found it very useful. So this is, it's not the direct SEM, but it's the backscatter image. It's a lot like an SEM image. And this is a silica aerogel with a metal copper particle in it. These nanoparticles, think about what size they were. So this scale is 800 nanometers. So this diameter maybe 400 nanometers. But we put in particles that were much smaller than that. So this is telling us that we are getting agglomeration, or the particles are all, collecting together, which is not necessarily what we want, but it's what we have. And then this is the EDX image, where we've asked it to just tell us where there's copper in this sample. And so it lights up in this case green, because we set it wherever there's copper. And so so that tells us that in fact is copper. So you see it's copper. And it's possible that some of this is the smaller nanoparticles that are what we actually put in. But it's also possible that this is just scatter in the signal. We cannot really detect that well. So could be that we have a lot of the particles, and then in some places they join together. Could be not. We're at the limits of detection for the scanning electron microscope in this case. But this is an example of sort of some of the information you can get from this. And you can see, again, a little bit about the pore structure. We often do it just to say, yes, that's an aerogel, that it looks like an aerogel. But you need to get in very close to do that, and that's hard to do. By close, I mean you're zooming in. What happens as you try to zoom in further and get closer and focus is because these things are so insulating, they get charged with the electrons, and then you get nothing. So that's a challenge. Okay, and then we also used this, both EDX and SEM, to look at structures in your sample. So not so much pores, we can't get to the pore level, but are there other things in the aerogel? And this is where we made a Ceria alumina aerogel, and we looked at it as prepared just after we had done the supercritical drying at it. And you can see there are some structure. This scale bar, oh, can't see this. Well, I think it's about 10 microns. So we're not very close in, but we didn't want to be. We see these structures here that are not normally seen in our aerogels. And so we know that that is the Ceria. And then the interesting thing is that after we heat treat them, and remember I talked about the pore distribution after heat treating for another project, we heat these to 800 degrees C. You can see some interesting structures forming in there that are different from here. And then we were able to zoom in on some of these structures. And now this is EDX imaging. Okay, so EDX imaging, and we saw something like this. So SEM and EDX allow us to see what kind of structures are forming. And there's this sort of very crystalline feature. And so we see it in, this is the backscatter, or like an SEM image. We see that. And then we use EDX to identify what it is. And so in this picture, purple is alumina. Okay. So it's aluminum. Green is Ceria. And then if we look down here, we have oxygen. So we have separate images of each. So this is all just the Ceria. This is all just the aluminum. And this is the oxygen. So it tells us that this, in fact, because we have aluminum and oxygen, is alumina. So this background is that alumina aerogel material that we made. And then we also can tell we overlap the Ceria and the oxygen. Sorry, the cerium and the oxygen, which means we have Ceria. So it's been very helpful in terms of looking at structures that you might have in your materials. You know, the pore distribution gives you pore sizes. If you don't get a whole, if you don't do anything to your aerogel, it's not particularly interesting other than to say it looks like an aerogel. It is very hard to get pore distributions from something like this because of the small area. But you can look at the structures that you see. And then when you start to add things to it, you can get even more information. So we really, as I said, we don't have the resolution here to tell us if we get the copper everywhere. So what we need, I'm showing one more picture. This is one more of the SEM, and these are copper alumina aerogels prepared using a copper salt. So we make the alumina wet gel, and then we soak it in a solution that contains copper, and then the copper infiltrates. And well, that's what we think happens. So we used SEM to tell us what happened. And this is alumina, which is a little bit easier to take images of. And this is, so you can see we're in very close. This is 200 nanometer scale is shown here. So you can you can see some pores, but again, you can't, it's very hard to get enough information to get a distribution of pores. But we also see these bright spots here, which said to us, okay, those are pretty small nanoparticles, at least we think they are. This is how the material was after we made it, and then after we tested it, which means we heated it, and we ran simulated automotive exhaust gas over it. And now this is not the same exact sample, obviously, but the sample looks more like this. And so these bright structures, which we believe to be the copper nanoparticles, are more pronounced. And again, when we do this, so this is, you know, a couple micrometers by a couple micrometers. It's a very small sample we're looking at. So when we do this, we have to look at many different locations, right? Is this typical of the entire sample, or is it only in part of it? So that's what we do. So this is typical of the location. And in this instance, you could extract some quantitative information by image processing this to identify what percentage of light spots are there, perhaps as a way of indicating the loading or how much of the copper you have in there. Because we have done some studies, you know, we take the wet gel and we put it in a copper salt, and that impregnates, it goes into the wet gel. We don't know how much of it goes in. We have done some studies where we look at the solution that it's soaked in, and we can use spectroscopy to say what is the concentration before we put the wet gel in, what is the concentration after, and we can say, oh, the difference is what went in. And another way would be to do something. We have not done that sort of image processing on this, but we could. And then this is another image of, I like this image. I think it's pretty, of a copper alumina. I always show it. Copper alumina aerogel. This is much farther out, right? So this is very close. These are similar aerogels. This is closer, and this sort of thing you can sort of see here if we went in close to see it. But here now, in this case on the left, these are just scanning electron microscope images. I think the bright spots are copper, but I didn't check. You know, we didn't check this. But here now we have, in fact, we looked at, we went in a little closer. Actually, I don't know if it's this image. This was just an image. I think somewhere in here we went closer. And here is that SEM image, again, with these bright spots. And sure enough, when we do the EDX on it, it identifies the red is all the copper. So we can in fact say, oh, okay, we do have copper nanoparticles. Again, note this here is, I think this image is just this part right over here. Okay, and this is 4 micrometers is this distance. So again, these are very big, I don't know, I don't know, maybe hundreds of nanometers. So it's hard to say exactly. But you can get that kind of information about the size of your nanoparticles that you're seeing, how many you're seeing in there. And we can tell, the other thing we can tell with this, and it's not on this image, but we can, oh, sorry. So we have oxygen here. So we see where the oxygen is, and there's probably, we didn't show alumina here, but there should be aluminum also. But we can see the red appears to have some of the oxygen in with it, which tells us it's a copper oxide. So we know the form of the copper that we get we start with copper metal in some of these, and we can detect that, oh, we get a copper oxide after we process it. Okay, I think my next. Okay, any questions on SEM? Any questions on that? So it's a technique that, you know, can complement the other things that we use for, like, the porosimetry. That gives us average information. SEM gives us very specific information, and again, more useful when you're doing things to, you know, we either look at it and say, yes, it's an aerogel, or we've done something to the aerogel and we want to know what we did to it. So let me get back to my, where's my screen?
Probably just in PowerPoint presentation.
Yep, okay, there it is. Okay, so I did say back up here, right? It's possible that these are all the copper nanoparticles that we put in there, about the size of what we put in, but we just don't have the ability to detect at that scale with the SEM. So another way to do that, to get better resolution, is to use a tunneling electron microscope or transmission electron microscope. People call it both. And so instead, where the SEM creates an image by detecting the reflected electrons, TEM transmits electrons through a sample to create an image. Okay, so it offers information on the inner structure of samples, such as crystal structure, morphology, and you can even get stress information, while SEM just provides information on the sample's surface and its composition. And so it's similar. There's a bunch of lenses and all kinds of things. There's an electron gun, which is much higher energy than an SEM, that gets shot through your sample. You can achieve very high resolution, but sample preparation is a little harder with a TEM because you have to take slices of your material. So for the SEM, we take crushed aerogel and we put it on a special specimen thing and put it in the SEM. With a TEM, you need very thin slices because you're going to pass these electrons through. So it's a little harder. We do not have a TEM. SEMs are very expensive. TEMs are extremely expensive. We do not have one, but we have just applied for permission and been granted permission to use one at a government lab in New York State. So we're going to be able to go and take our samples. And we want to take our samples and see if we can see those metal nanoparticles. But I have some pictures of that's some from a reference down here where they did a TEM of silica aerogels. And this is an image, it images a slice of the sample. So here, this is 100 nanometers. You can start to see that sort of structure they talk about with the aerogel, right? The chain, the linked chain, and you can see that. These are just two different types of aerogels that they looked at, but you could actually see those colloidal clusters of silica, you know, and you can see the size of them. This is 100 nanometers. These ones look, maybe they're 30 nanometer diameter, and you can start to see pores, right? You can now see pores in the structure. So it gives you great detail when you look at something like this. Again, this is just a one slice, one little slice. So you can withdraw, you know, on a slice, you could try to generate some pore size distribution, right? You could measure these, all of these. In fact, in this reference, what they did is they took a bunch of slices of aerogels using TEM, and then they stacked them together to make a three-dimensional structure of an aerogel using this information. So this gives very nice information. And so what we hope to go this summer is that we will see something like this with our alumina aerogels, and we will see perhaps the small copper nanoparticles. It would allow us to better see this, right? We will have the resolution to look at something like that and see how we're interested in knowing how the particles are distributed and how big they are. So the size is very important in catalysis applications. We need to know how big, we want to know how big they are and how distributed they are. So we're excited to be able to do that because you can get some very good information. Okay, and then the last one I'll talk about is atomic force microscopy. This is another sort of high resolution, but it's not optical. It uses a scanning probe instead of optics. So it's not taking images. It's taking a probe that it takes across a surface. It can resolve features, again, at the nanometer scale. Can also be used for force measurement, so people use that. People use it for manipulation to make things, and also topographic imaging, which is what we use it for, so I'll show you that. And it results in, I call it a 3D image. Again, it's a small part of the surface. I have a sort of picture of how, being a mechanical engineer, I better get the pictures of the mechanical parts than the optical parts of the electrical engineers. This one makes much sense to me. So basically you have a cantilever with a probe on the end. Okay, it's a tip, right? This is just the support for the cantilever. This is the probe, and the probe is important. They're different. They call it the tip. It's a probe. It's important. There are different types you have to set depending on your material. Then it's got a piezoelectric element that will oscillate the cantilever. It's got a detector. Sorry, there's the probe and there's the detector. Here's your sample. Here's your stage. You lower your detector and then you pull the stage across. And so the little probe goes up and down. And the detector here detects the deflection of that probe. And this is all, it's very, we do have an atomic force microscope at Union. It's a bit finicky to use. It's difficult to prepare your sample. Again, you have a small sample. You have to adhere it to, you have to make it stick to the surface in some way. But we were successful in, so there's two images here. The top one is a silica aerogel. This is not ours. This is from the literature. And this is the sort of thing you get. The bottom is ours. This is our copper alumina. But these are the sort of images you get from AFM. And so for the silica, we're looking at something that's like 400 nanometers by 400 nanometers. The color tells you the height. Okay, so in this is at 0 and this is at 100 nanometers. So you get, I called it like a 3D image. You get some depth information from that. So you start to see, so certainly you start to see some pores here. And then you can see the size, and this looks to be about 100 nanometers. This is that colloidal silica part of the group of silica atoms that joins. And so it's a nice image to see that. Ours here is one we have for our copper alumina. Again, you can see the same sort of things. This is a little higher magnification. So we didn't get in as close as they did, but you can see the same sort of structures that are forming, and you can see some depth and some height. And in fact, you can plot it sort of like this to give you a sense of the scale. on this. This was, this is a better image that the student who did this had to figure out how to adhere the aerogel to the surface without having it move, because you take the probe and you move it across the surface. And sometimes when you do that, you'll see some smearing, maybe here. So he used nail polish, what people put on their fingernails, is what he found would attach it well. So that worked well. So we were happy to get this sort of information. Any questions on any of these techniques?
Looks extremely similar, like the LP reader from music. This one. The principle is exactly the same.
It is exactly the same. Yeah.
You got a signal that you are fine for the differences.
Yes, exactly. It is exactly. That's what they use. Maybe they can play music from AFM.
Yeah.
I don't know. I don't know.
We may try. Anyway, I got a question about this. The possibility to detect the copper particles.
Yes.
Yeah, that one. Okay, I can see the point that we cannot be sure
Yes.
about the origin of the signal from the signal about all the scattering points that are surrounding the main points, but the main area. Let's see.
Yes.
The point is that once we have got the transfer function of these points, it is I think it is possible to create a filter for the frequency of the copper.
Yes.
And then try to filter in the impulse response and try to see in the timeline if there is any reflections in that point or not.
I think we could too. We have not done that. I think we worry that this just isn't the way to do it. And that's why we want to do TEM.
Oh, okay.
Because that's what we've focused on is trying to get to do TEM on it. But I think you're probably right. I think that is not just scat. I don't think it's just noise. And I think you're right. We could try to remove that to see that. But our focus has been on trying to do TEM because there it's unambiguous.
Yeah.
You can see things, if you go to this image. Right. We're looking at, we will easily detect 10 millimeter. Many other people have done this with nanoparticles in there, so we know we can do that. So that is our focus. We're going to try to do that this summer. And down near New York City is the location.
Sure.
Okay, so this just summarizes the kind of things you see with the different techniques for imaging. Right, so we can use these methods to learn more about the structure. And they said they generally involve, they're very expensive equipment. Most people share, many people, we have one of these, and they are used by many research groups on campus. So, in order to do that. And we have extreme needs for aerogels. They're very, very hard to see at this scale. We have people in geology who study rocks, and much easier to image, so they don't have any trouble with it, but we do have some. But these are the sort of different things you get from the different imaging methods, right? So kind of the overall, what does the material look like? Here is what's a kind of a slice, and it's much smaller scale. And here is a little bit of that sort of 3D image. These are all silica aerogels, so I put these all on in. But the different things you can learn using those techniques. Okay. Okay, so that's imaging techniques. We'll take a break in about 10 minutes, but I'll start on the mechanical behavior of aerogels. So, most people think of aerogels as fragile, and they are. So we can describe them in terms of elastic. They can be elastic, which means they deform and come back. Fragile, like glass and ceramics, but they also have plastic, behave plastically, where you deform them and they don't change back. So there are a bunch of different techniques that are used in the literature. I have not used all of these, I've used a few. But there are many ways you can characterize aerogel mechanical structure. There are dynamic characterization techniques using ultrasound or dynamic mechanical analysis, and I'll talk about those two. And there are additional ones, these are just two I'll talk about. And you are measuring elastic properties. And the elastic properties of interest are things like we call Young's modulus. It's a modulus of strength. I'll define on the next slide these. Shear modulus and Poisson ratio. And those things can also be measured using static techniques, which include things like 3-point bending, uniaxial compression, and they give us some elastic properties. So I'm going to talk about these different methods. But before I do, I will define, how do I get rid of this thing? No. How to get rid of that? No. Well, I guess they can see it. You can see it. Oh.
Yeah, this is, okay.
I don't know what I did. Okay.
It's
So,
work.
yes. So there are different moduli. We call it a modulus, elastic moduli or modulus that are used. And so the symbol E is used to represent, so E is the Young's modulus. Okay, and it characterizes the longitudinal deformation of the material subject to longitudinal stress. So as I pull something, how much does it deform based on how much I pull it apart? The other ones I'm not really going to talk much about, but you could talk about the shear modulus, which is related to shear strain, the other direction, and the bulk modulus. Poisson's ratio is something that measures the deformation in a material in a direction perpendicular to the direction of a force. So if I have something and I push on it this way, how much does it go out that way, right? So I squeeze it down. Does it extend that way? It's dimensionless, typically ranges between 0.1 and 0.45. I've never measured nor used this number, but I've read that silica aerogel people report about 0.2. And you can relate all of these different moduli. So if we measure this, and this is typically what we measure, we can then calculate the other things using the Poisson ratio. So mostly I'm going to concentrate on the measurement of this. Right, so knowledge of two of these things, either Young's modulus, shear modulus, bulk modulus, and Poisson ratio. If you know two of them, you can get everything defining elastic response. But the main measured elastic modulus is Young's modulus. And so that's the one we'll talk about. Okay, so when we're characterizing something mechanically, here would be a sample, and we pull on it. That should be perpendicular. We're just pulling on it perpendicular to the sample, and it will deflect, right? It will stretch out in some way. So if its original mount length is L, we pull on it with force F, and it stretches out by a distance dl, delta L. We can calculate the strain, which is the change in length over the original length. So that is what we define as strain. The stress that we put on that sample is just the force divided by this cross-sectional area. Okay, so it's cross-sectional area. So it's force per unit area. It is like units of pressure. Okay, so we characterize materials by looking at a plot of stress versus strain. And this will look something, typical material will, as you pull on it, it stretches, 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 stretches. And then eventually it yields. And so this first region is called the elastic region. So if I pull it and I release the force, it goes back. So that's the elastic region. And so it's a non-permanent deformation. Once you reach the yield stress, you go into the plastic region, which now if I pull on it, and also I should say I can pull or I can push, either one. So pull or push. Now if I pull past this and I release, it doesn't go back to its original shape. And so that's a permanent deformation. So we define the elastic modulus of an object as the slope of its stress strain curve. So right here, okay, the slope of this curve is equal to a material's modulus of elasticity or elastic modulus, both are used. Again, the symbol E, sigma over epsilon, stress over strain. And so that information, though, is taken at very low strain rates. And I'll show you some deformation plots for materials. A stiffer material will have a higher elastic module. That's what I see on this. Okay, so what we do? All right. So when you're looking at aerogels for load bearing, you really need to do a fair amount of mechanical characterization to figure out if it can behave in whatever application you want. And there's a reference down here in the aerogel handbook about good ways to characterize aerogels mechanically. So you might want to design experiments that are going to produce the same loading conditions that they would be in service. So if you're using aerogels to do something, you're going to want to understand if they can take the forces on them. And so again, what they're recommending is probably multiple types of tests are what you're going to want to do with aerogels, whether tension's hard to do with aerogels, compression, torsion and bending are also hard. Well, in this section, I'm going to talk about how we can character the mechanical characteristics and how to characterize them. And then I'll also talk about some of the things that people have done to make stronger aerogels. And those can be, in those applications, so aerogel composites, you can do many of these types of tests. Okay. So one type of test is a dynamic mechanical analysis instrument where you want to determine the stiffness or the strength as a function of maybe of temperature. And so there is a device where you can take a sample, and this is 3-point bending. I'll talk more about that in static tests. But 3-point bending is you have a sample, it is supported at the two ends, and you apply a force here. And so in a dynamic mechanical analysis system, you simply push, release, push, release, push, release, push, release. And you can measure that signal to get some information about a sample. And they do this on aerogel samples. Another dynamic analysis is to do an ultrasonic test. And so you can have an ultrasonic pulse is generated by a transducer, and it's sent through the aerogel specimen. And you could either have you could have the transducer be the transmitter and the receiver, or people have both, one on each end, but you can do both ways. And so from the sound velocity of the waves, knowing that, the density and Poisson's ratio, you can calculate Young's modulus from that information. So this is a nice non-destructive method for determining elastic modulus of aerogel materials. It does not, the other techniques tend to destroy your sample, but this does not. And so this is just some early data from this reference here, where they used ultrasonics to characterize silica aerogel of various densities. Okay, and here is the sound speed through that. Right, so they're getting the sound velocity as a function of density, and it goes up as it becomes a more dense material. And then from that, they have determined the elastic modulus. So more dense, the stiffer they become with the higher modulus. Okay.
So again, it's linear for the boom density, but exponential for the
because it's got it's got the velocity squared. Yeah. So it's related.
Sense. Yeah.
And so these are very low. Again, this is sort of where you are with the kind of silica aerogels we make their way down. They're down here. We'll go ahead and start again. Hopefully you can hear me, and I've shared the presentation.
Yes, we can hear you.
Okay, good.
We can see the presentation.
Good. Okay, so among what's considered another technique for testing these materials is called three-point bending. Because silica aerogels are pretty brittle, it's difficult to test them under tension. I'll show you an example of tension. You're pulling them apart, very hard to do. Torsion, you're twisting it, and that's hard to do. So what is the main way to test these things with these so-called static tests is by flexing them, or bending them in this, and compression tests. And so the flexural strength can be used to estimate the tensile strength of a material. Again, that's back to the Young's modulus. And so here's a closer picture, an actual image of that three-point bending that I showed before. So here is a sample. Sorry, this is my sample under test, right? This is not an aerogel, obviously. This is a piece of metal. So it is here. It is supported on each end, and it is loaded with the force in the middle. Okay, so that's why it's three-point bending. 1, 2, 3. So you can relate the information you get, which is basically the deflection of the material as a function of the applied force, to that modulus, right? So F is the force that you apply here. L is this distance across your sample. Y is the deformation, how much is it pushed down? And you can relate that to the modulus. So that's done. You'll see quite a lot of papers in the literature of people doing testing, this sort of testing on silica aerogels and other types of aerogels. Now, we don't use it, but it is a fairly simple test to do. The method we use is uniaxial loading. So you load your sample in one direction and we compress, we can't pull. So these are just a bunch of machines from a company, MTS, and we have one of their smaller ones, more like this. But these are just big structures, metal structures here, and you would load, let's see if I can see a good one. You would load your sample in here, and you can pull on it. And what these things do very accurately is you set the force you want to pull with, and then it measures the extension, because remember, to get the strain, we have to know how far you've pulled it. And so it's important to get that information accurately. And so tensile testing is something done on many types of materials where you test them in tension. So you're pulling them out. And you typically use a dog bone shape. So some pictures of what I mean by dog bone. Looks like a dog bone. Something like this are set by, there's a lot of standards about the shape of your material, the dog bone shape, how it necks, etc. There are many standards on doing this. You really can't do this for a silica aerogel. You couldn't. You then clamp the ends of your dog bone between these two clamps, and then you pull. You slowly pull at a slow rate. But I did find somebody who did this with cellulose aerogel, so they're much different, and they were able to make some measurements. But this is this classic industry standard for most materials, is to test them in this way. But it just doesn't work for silica aerogels. What does work for silica aerogels is to apply a force and use compression testing. So here's sort of a close-up of one of these machines in here. They have different, this is sort of a gripping thing for pulling apart. I don't see a good picture. This one may be for compression, but you can buy different fixtures that go in the machine. And in this case, there are two parallel plates, and there's a sample, almost looks like an aerogel, but I don't think it is an aerogel. It's just a picture from this company's site. And then you can apply a force, and you can measure the stress. You know what the force is you're applying, you know what the area is, and you can get the strain, because you also have either in the electronics in the device or using something called an extensometer. You can just simply measure how far the plate moves. And from that, you can construct for an aerogel a stress strain curve. And this is a typical stress strain curve for this is a silica aerogel. It's a little bit dense. Again, typically it's about 0.1, so this may have been heat treated or something like that. It's a little denser. And then they're just comparing to a vanadium oxide aerogel also. The comparison is not relevant for my purposes. I want to show you what happens when you crush an aerogel. So looking at this, so again, remember kind of your typical material. You have this elastic region, yield stress, plastic region, and etc. And for an aerogel, it looks a bit different. You sort of have an elastic region. Okay, and then you go up and you get, we call it a densification region on the aerogel. When you measure your elastic module, it is down here at very, very low strains. So if we look at an aerogel, kind of a description of what's happening with the aerogel, you get a behavior that looks a little bit like this. You have a linear region. So they have sort of a linear region down here. And then you have sort of something going on, which we attribute it to the pores collapsing, right? And mechanically, you can think of those pores and the pore walls as being beams, and they're breaking. And then you get a behavior like this, which is due to densification. The material is just getting more dense, right? You have the same mass, but you're crushing it. Now I'm going to show you what's happening with an aerogel. So when people measure, you measure the elastic module down here. You get sort of a linear region here, where you would estimate your elastic module. But in here, you get this pore collapse and then densification. So this is a silica aerogel. This is from my lab. This is a compression tester. So there's one side and there's the other. This aerogel is about 20 millimeters in diameter and maybe 15 high. One of the issues with doing these tests is You need to make sure, and it's very hard, but you have to make sure you have flat surfaces, flat parallel surfaces to get very accurate measurements. We weren't, this is not perfect. We would sometimes sand them. We weren't trying to measure elasticity. We were just trying to see what happened with an aerogel. So we weren't so concerned with that. And so I'm going to run this, and the top platens are going to come down, and you kind of see what happens to an aerogel as you crush it. There's also, the light is slightly polarized, so you can see, you'll see changes in the color. It kind of crushes. I think we're probably applying around 5,000 pounds, 5,000 newtons. So you see it kind of crushes, and then it starts to break off. Pieces chip away. It's still there. You can see, and it's getting denser. You can look at the color. But it chips and it chips and it chips and it chips. It is not particularly strong. But surprisingly, there was quite a bit left at the end. You can see down that, well, if I move that way, there's a little bit left at the end, but it really chips away. So this is not a particularly strong aerogel. This is a project where we're trying to strengthen some of them. And I'll get into where some of that happened. But one of the things we looked at was a study of what happens to the aerogels, what happens to the pore size of the pores in the aerogels as you crush them. So we did some testing on these cylindrical aerogel samples. So 23, so 23, so it's a cylinder. It's 23 millimeters in diameter, 19 millimeters high, and it weighed about 0.7 grams. And I think the density of these is about 0.1 grams per centimeter cube. And so we loaded them to 1, 2, 3, 4, and 5 kilonewtons. And we looked at pore distributions using gas absorption, like the stuff, the thing I was talking about yesterday, to look at what's happening to the pores as you do that. And here are some, this is not stress versus strain, but it's related to stress versus strain. This is the actual load, and this is the extension, how much you move down. And we can convert this to stress strain, but I didn't. In this case, this is when it was loaded all the way up to 1 kilonewton, and this is when it went up to 3 kilonewtons. So it just shows those curves. And this was, actually, I wish I had a side view, but this is what happened when we loaded the sample. So from above, so no load, it's perfect cylinder, right? 1 kilonewton. You saw in that video, stuff gets chipped off. 2 kilonewtons, 3 kilonewtons, 4 and 5. And what you're not seeing is how little these things got. And you can see some color variation, I think, is just due to it's an artifact of the camera. Doesn't mean anything. It's just the way the pictures were taken.
Oh.
So yeah,
So
yeah.
there is no
I know it doesn't mean it.
the light of
They do get denser. So there's some of that, but no, we didn't carefully control that. So you can't tell anything from the color of that. And so here's, in fact, some of the results we got that we found. So this is, remember from yesterday, this is that pore distribution, the volume of pores. Again, this is plotted per nanometer. This is a slightly different way than I plotted yesterday, but same idea, volume of pores versus the pore diameter. And so when we went with 1 kilonewton loading, these are multiple samples, the maximum was about, the average was in the 20s somewhere, similar to the 0. But then when we load as much as 4 kilonewtons, you can see two things. One is this peak is lower, so there aren't as many pores. And 2, the average pore size shifted to the left, so smaller pores. So there's variation in the samples that we have. more for these than for these. But we see a change from, say, 20 to 24 nanometers for the 1 kilonewton sample, and about 12 for the, this is for the 4, but for the 5, no, this is 4. No, sorry, this should be 5. That's 5 kilonewtons. Anyways, these are sort of the differences. So we see what's happening. And then this is a picture. I showed this picture before. This is an SEM image before we load it, just as we made the aerogel, what it looked like. And then this is what, these are the roughly the same magnification, 1 micrometer, 1 micrometer. But here it looks very different. You can see that we've crushed them. It looks denser. Right? The aerogel part looks much denser. Again, we can't really get information about the pore distribution from this because we're only looking at a small area. But here, it does look like the pores are smaller, but I can't get the quantitative information that I can with this. And so we did a nice thing with that. And these, in fact, I showed this yesterday as an example of where we used gas adsorption. And these are now, instead of in terms of load, we're using final pressure on the sample because, or stress, because these get smaller. Well, they stretch, but we lose material. So instead, we calculated the force divided by the area at the end of testing. Okay, because it's really that stress that matters. So this is the stress on the material. And from yesterday, remember when we don't, this is the isotherm. No loading, you have your maximum volume adsorbed. And then that decreases with loading. And then the other thing here is that I mentioned yesterday that the location, so this is adsorption, desorption. The location of the hysteresis, the closer to saturation, the bigger the nanoparticle, or sorry, the pore size. And so you can see as we crush it, this hysteresis is moving to the left, which agrees with this plot, which shows that our pores are smaller. So that's sort of, you can understand that qualitatively from the isotherm data. And then when you perform the BJH calculations, you see, in fact, there what's happening. And so we plotted pore diameter. This is average pore diameter versus the stress, and the pore volume versus the stress. So we saw the trend. And in fact, we ended with being able to say that the maximum pore diameter, so what was the biggest that was left? We didn't do the biggest, but we did something related to these distributions. We didn't quite use the average versus the stress on the sample. And we got a nice, logarithmic relationship, which agrees. So the diameter goes like the pressure to the minus 1/3 power, which agrees with some other data. So that was interesting to us to understand what was happening to the pores as we loaded them and crushed them. We didn't do anything. If we do that, obviously things like thermal conductivity, everything is changing, density is changing, etc. Okay, so this is a plot of just giving the strength, some information on the overall strength of aerogel. This is that Young's modulus, and this is density. So fairly well-known relationship between modulus and density. It's a slope around 4, 3.6. So, and this is a log plot, so that means modulus goes like density raised to the 3.6 power. And there's a whole bunch of different aerogels on here. The silica in purple. Again, down, and the density of the typical ones that we make is in this region. So low modulus, and as you make them denser, it increases. The green is for silica for sintered aerogel, which means it's been heat treated, it's densified a bit, a little stronger. And then there's some other aerogels on here. There's some resorcinol formaldehyde carbon aerogels, and there's some other carbon aerogels. But so this gives you the idea. Again, the takeaway of this is aerogels fragile. The more dense they are, the stronger they are. But the more dense they are, then you also lose some interesting properties like surface area and low thermal conductivity. So I thought I would just talk a little bit about, so there's a lot of work to make stronger aerogels. Now my focus is mostly on transparent silica aerogels, and you really can't make them stronger without changing the transparency of the aerogel. It's very hard to do. At least no one's done it yet. So we just put them between glass, and that's how we strengthen them. So there are sort of three basic ways to strengthen those aerogels, and their methods are chemical cross-linking, fiber reinforcing, and then reduced bonding on the chemical structure. So I'm going to go through those and show you some examples. So, and this is a picture again, you know, aerogel can hold many times its weight. That's just a silica aerogel with a brick, and it looks just fine, but an aerogel does not weigh very much, so that doesn't mean a lot that it can hold, you know, 10,000 times its weight. And you saw from some of the things I just presented, they do hold well in compression. So the cross-linking, and there's a lot of work in this area, they're called X aerogels. And this was developed out of NASA, the space agency in the United States, and some people at University of Missouri. And so they often add or dope materials, they dope plastics with different materials, oxides, fillers to make them stronger, right? Familiar. So some of the researchers in this area, particularly Nick Levantis and Marianne Meter, tried to do that with something like that with the silica aerogel. So they took a gel, just a wet gel like you would for making a silica aerogel, and they soaked it in solutions containing, I think they use diisocyanates to cause some cross-linking. These are materials used to make varnish. And then they heated the gels to get these things to bond. Then they supercritically dried it, and it resulted in, these are some pictures of some of the first studies they've done with this, where the aerogel, again, it's not transparent. You completely lose that. It's opaque, but you can start to bend it, and you can do more with it. And there's been, since this initial work, there has been a lot of work looking at cross-linking aerogels. And here's some of their studies, and this again is from the Aerogel Handbook. Here's an actual aerogel in 3-point bending. I showed you before was just a piece of metal. So here's an aerogel under 3-point bending, and they looked at stress at break point with this. They're looking at this out here, right? They loaded it, and let it break. These are just different types of cross-linked aerogels, but compared to, this is when they say native, they just mean a regular silica aerogel, right? So the regular silica aerogel is going to break at a much lower force than these cross-linked. And so they're able to show how much stronger that they are. So there are some commercial products out there that have taken advantage of these, this idea of cross-linked aerogels. I believe both of these are polyimide-based silica aerogels. And so there's a company called Blue Shift Technologies that makes, it's called Aero Zero. It's a film. And these were all developed at our NASA space agency. And these are small companies have licensed their technology to make these sort of films of aerogel. Airloy is another one. This is a stronger material, aerogel based, but again, not at all translucent. These are used, these are interesting of use for acoustic panels, things like that. They use them, they're trying to put them on airplanes as insulators because again, they're very lightweight. So they're an interesting new product based on a lot of this work to strengthen an aerogel.
Huh. So they got a high group density, I think, or not?
They're higher. I have the, yes, it is higher, but it's still pretty lightweight. So I don't have the exact numbers. I was going to show you this, this material because it's actually fairly robust. Another way is to use fiber reinforcement. So if you impregnate your wet gel with some kind of fiber, you can make a composite material. This is one from Aspen Aerogel. Other companies make the blankets. They're not the only ones. They are one in the United States. So I think they may have been the first to do this, though, I will say that. Developed a method to cast your silica gel onto a fibrous batting, so a fibrous material mat, and then supercritically dry it, and they use supercritical drying to produce reinforced aerogels. So it is almost as insulating as the plain aerogel. It weighs a little more, but it can be rolled up. And I think these are more insulating than these materials, but I'm not certain. These are quite insulating. So they are technically a composite aerogel material. And this was the video I showed you before of just a regular aerogel. And now I have a video. So I had a student, we didn't use the same blanket material that they did, but we tried a project where we used chopped fiber glass wool. So the thinking was glass wool, because it will not be as conductive. The material may be, we did increase its thermal conductivity, but not by much. And again, you can't see through it, but here's an example. So that one, you saw everything chipping away. And this one, we're crushing it, but now it's not chipping. It will chip, but not as much. So it chips more at the end, but the fibers in there keep it together. And that's why this is one of the techniques used to strengthen. I don't know what happens at the end. I think it just goes back. It shows you. So it's able to still gets crushed to nothing, but it doesn't start to chip away in the same way that the plain silica did. So the technique that they developed, which is interesting technique, is they would make it by, they mix the silica precursors together with their catalyst and any dopants. I think they put some dopants in to help with radiation. And then they apply it to a fibrous bat. So this is the batting. This is like the woven material. Right? They put it on the woven material. And then they let that gel on the roller. And what was unique about this is the ability to actually roll this thing up, because who can roll in it? You can't roll an aerogel, but you can roll like a blanket. But then they roll it up and they put it in, they do supercritical drying in a big vessel. I have not visited this location, but many of my students have, and actually one is going to be working there. I've seen pictures of these big pressure vessels. They do some aging, and they do carbon dioxide supercritical drying. So they remove, because they have a big system. you know, and then they dry it and then they roll it onto these rollers and they ship it. So it's an interesting approach to making aerogels. I think this company was one of the most successful in the United States for actually commercializing the use of aerogels. So they are used a lot in oil pipelines. That was their big market. They would wrap the pipelines with this aerogel blanket material. Again, it's easy. You can form it to anything. It maintains a very good insulating property. And it's also, there's been more work in this area with many other companies too. These guys were just one of the first. But the comment I would make about this is they are not the greatest to handle. The powder comes off. Like if you know, the aerogel powder, they're powdery. So they have to be encased in something. Otherwise they're powdery. So I don't, you know, like working with them, but they claim they can bend them and they don't lose much. But they're a good product. And I know there are many other companies looking at doing this sort of thing. So, and then the other way to make the stronger aerogels is through reduced bonding. I think I showed you this picture of a flexible aerogel. Here's another picture of that same type of aerogel. Here's the aerogel. Normally it's in a tube. Then he pushes down on it with a pencil, crush it, and takes the pencil away, goes right back to where it was. And so the way that this was made flexible was reducing the amount of bonding. And Professor Carroll talked a little bit about this with hydrophobic aerogels. So normally you make a silica aerogel with the TMOS, the tetramethyl orthosilicate, or the TOS, tetraethyl orthosilicate. And you have the silicate atom with 4 oxygen bridges that connects to others and connects so on. And it makes this rigid structure where these atoms, the silicon atoms, are highly mechanically constrained. If instead you make it with methyl trimethoxysilane, MTMS, or a different starting precursor, you do not connect 4, you connect 3 or less with these. And Professor Carroll talked a little bit about that. So then it makes something that is more flexible. It's just not rigidly bound. So the idea of stronger aerogels is these are just flexible aerogels by changing the way they're structured. And again, these are not, they're opaque is what happens when you make them like that. So that is sort of the third way to make them. Any questions on strength characteristics or stronger aerogels? There's a lot of work in this area. I think they're doing graphene doped, all kinds of things where people are trying to make them stronger. But as you can see, well, there's 2 things, and I'll talk more about that, is that you lose transparency if you care about it. If you don't care about it, it's a great way to do it. But you can also lose some of the insulating properties, which can be of concern. So any questions on that?
Yes, I have a question.
Yep.
I know that maybe the answer is different from type to type of aerogel that you showed us, but I didn't understand how much percentage of aerogel is in this kind of composite. Is like the 90% of aerogel and 10% of fiber,
Yes.
or
Yes,
the opposite?
it does depend, obviously, right? It will depend on the type. It'll also depend on whether you mean volume or mass percent, right? Because for the aerogel blankets, the aerogel doesn't weigh anything, right? So its mass percentage is probably quite small. I would say, based on looking at them, its volume percentage, there are different versions of, I would say it's 30 to 50% by volume. I think, so, I mean, you are right. The answer to that question is it depends. This here, I think we did, under 10% by mass of the starting precursor chemicals. So when we do this sort of thing, we start with the chemical mixture, but after the fact, you know, by mass, it's hard to, the glass wool fiber weighs much more than the aerogel material. So it just depends on the different cases that people use. And I think that's often what people do is you vary the percentage of whatever you're filling with, and you look at a trade-off between its strength and the thermal conductivity, right? The more of this other thing you add, the stronger, but the less insulating it will be. So there is a range out there.
Okay, okay. Thank you.
Yep. Any other questions? Okay. I'm going to just the last, but I'm going to talk about spectrophotometry, mostly just talking about, we're very interested in looking at visible light transmission. So I'll talk a little bit about some of those results, and then we'll stop because the next thermal will take much longer than what I have time left for. So I have a few slides on this. So basically, you can measure the light passing through a sample. So in this case, you know, you have some sort of light source with a lot of optics included. It passes through a sample and you have a detector on the other side. And so we are mostly interested in the light in the visible range of wavelengths, but you can also gather information at much higher wavelengths, which will tell you a lot about the what's the structure of your aerogel. And so we've done, so we've done some, so for example, we've done some work. We tried to make more hydrophobic aerogels by combining the regular method of making them with this methyl trimethoxysilane, some ethyl trimethoxysilane, and some phenyl trimethoxysilane. So these are the different sort of co-precursors that don't permit all of the bonding to happen. And as a result of that, they become hydrophobic. So we were interested in making hydrophobic materials. We weren't as concerned about the transparency, but that is in this study, we just want to see if we could make the hydrophobic material. But this is the different chemical precursors used to make them hydrophobic. And this is the amount by volume that we put in the recipe. So this is just TMOS, and it's fairly translucent, and it's what we measure with the spectrophotometer is the amount of light transmitted versus wavelength, and this is the visible range. And so here's what we get. These are 12.2 millimeter thick samples. And so not a lot of light, but it approaches 80%. This is the visible. But once we start to add these precursor chemicals that make it hydrophobic, you can see it becomes more opaque, right? So here's where we added 25%, and here's at 50%. So it really lowers the amount, and you can see, you can't really see through that, lowers the amount of light that you're able to transmit through it. So this is sort of an example of using spectrophotometry to understand the transmissive powers. You get a lot of, what's happening here is you are scattering the light because they're the small wavelengths. At low weight, because of the pore structure, right? The size of the pores is like 20 nanometers, so you get a lot of scattering. But a lot of the work we do now is with these thin aerogels. I showed this picture. And so now we have transmittance. And so what's shown here, the amount of light transmitted is a function of how thick it is. The path length matters. This is transmittance values for 15 millimeter thick, 5 millimeter, and 3 millimeter thick aerogels. Now these two were made with a different chemical recipe than this. So in addition to path length, we have chemistry going on here. We use more catalyst here, and it gives us, this here is this 5 millimeter thick. You can see it's very transparent. So if you calculate the average transmission from 380 to 720 nanometers, which is your visible range, we go from 42 to 94% on these. So these are really quite nice. So we've been using, we use spectrophotometry in the visible range, but you can also, and I don't think I did any more now. You can also use it in the infrared and the U. Well, that doesn't pass anything in UV, but in the infrared, you can determine information about the bonds and what's happening in there. But that is, well, all I have today. I think I'll stop here. I have some things on thermal, but it will take me, I could not possibly finish in 3 minutes, even if I talked at my normal speed. So I will leave this for next week, and it will go right into actually leaving off on the spectrophotometry, doing the thermal, then talking about aerogel windows, which is what I will do on Tuesday. Are there any questions?